So welcome to the second session on feedback control, machine tuning, and optimization track. My name is Marco Lonza from Elettra, Italy, and I'm co-chairing this session with Enrique Blanco from CERN, Switzerland. In this session, we have 4 interesting talks on machine learning and Bayesian techniques. The speakers, we have 12 minutes for the talk, followed by 3 minutes for questions. So we will warn the speakers after 10 minutes from the beginning. We remind the audience that they can ask questions by raise hand button on Zoom, so we can enable your microphone, or by writing the questions into the WUVA Q&A. Okay. So the first speaker is Luis Vera Ramirez from the Helmholtz Zentrum, Berlin, Germany. The title of his speech is Machine Learning Tools Improve BESI2 Operation. Luis took a BSc degree in mathematics at the University of Zaragoza, Spain, and an MSSC in mathematics at the Berlin Technical University. After some years in the industry, since 2018, he is data scientist at BESI2 in the Accelerator Operation Department at the Helmholtz Zentrum, Berlin. Please, Luis, share your screen.
So I'm going to share right now, and I hope you can see my screen. Can you? Good. Yeah. Great. And it moved right now. Okay. So first of all, thank you very much. Thank you to the chair, organizers of the ICALEPCS. And good morning, good afternoon, good evening, depending to everybody attending the conference. The aim of my talk is to make a small report on the machine learning development towards operation improvement at BESI2. In particular, I'm going to focus in 2 cases that are actually work in progress and where we're putting a lot of effort. For those of you that don't know BESI2, this is a light source, a synchrotron located in Berlin-Adlershof. You have here all some of the parameters, a circumference of 240 meters, and it has 1.7 gigaelectron volt of energy. And we have almost about 5,000 hours of measured time per year and about 3,000 user visits. Regarding machine learning, we have been putting some effort on this on many cases since 2018-19. In last ICALEPCS, I presented some of our first use cases, which was some prediction cases, booster codon and injection efficiency optimization with reinforcement learning. We have also a nice team working rather at the beamline on experiment site, led by Dr. Georg Hartmann. They have also very nice projects regarding beamline ray tracing inversion, or a very impressive project regarding data compression with latent space labeling. And they are writing right now some papers on the topic. And finally, what I'm going to present today, as I mentioned before, the 2 cases we are putting at the accelerator side more effort right now. The first one is the mitigation of harmonic orbit perturbations, mainly with reinforcement learning, but also exploring other areas. And also a new project regarding anomaly detection with some new techniques in order to make future assignation. I start with the first case, the mitigation of harmonic orbit perturbations. For those of you working at accelerator, you know that the beam stability is a very, very crucial parameter. The beam has to be as close as possible to the theoretical orbit. And this is a parameter that has an enormous influence in the quality of the light and the user operation. At BESI2, we have a nice algorithm running for a few years, almost 12 years, this reference there. It's a fast orbit feedback system based as many algorithms, as many systems, and the response matrix based correction. It means, roughly speaking, you calculate or you measure your response matrix, which maps the response of the BPMs, beam position monitors, to the modification of the magnets of the steers. And with the inverse of this matrix, you can iterate and correct your orbit. This is a nice system. This works really fast and really fine, and it corrects in a very efficient way the static perturbation. Let's say this distortion of the orbit due to magnet, false position of the magnets, and so on. But the problem is that at BESI2 and many other accelerators, we have external perturbations, in this case, civil noise, the 50 hertz of the main power perturbation. And we have also some imperfectly isolated sources, and also the fast orbit feedback itself. You can see this here. It induces some extra perturbations in the orbit. This is a problem that I have been faced at BC2 by Oliver Shortloff a few years ago in his master thesis from an analytical point of view, and we decided to face this problem with machine learning. We conceived a reinforcement learning agent that interacts with the environment. The environment is the accelerator itself. It's a reaction of the orbit to the modification of the steers. So the idea was to use reinforcement learning in order to mitigate this harmonic perturbations. We started last year with some simulations with Oliver Shortloff, also with Ocelot. And in last year, we started with our first test of the machine. And after some, of course, logistic problems and the effort to establish a good connection, we ended up with some results that I'm presenting today. The first approach for reinforcement learning is a model-free approach. What does it mean? It means the agent observes something, the state. The agent proposes some action, some modifications of the environment, which is the action, and it tries to maximize the future reward. In our case, the state is the last readbacks of 6 BPMs. The action is the strength of 6 steers. They are chosen according to that to high correlation. And the reward in this first case, which is a toy case, is the distance, is the perturbation, sorry, is the deviation of 1 BPM. This BPM is chosen because this is the one used at BC2 in order to measure the beam motion. We work with the DPG, the deterministic policy gradient, which is a well-known reinforcement learning algorithm, and compare with some baselines such as doing nothing, letting the steers in a good position, our standard fast object feedback system, and our implementation of the system in our reinforcement learning loop. You can see here a first learning process and convergence here. We have some alternation between exploration and baseline. And you can see that in time domain, the red line, which is the reinforcement learning agent, makes a good job. It's an easy case. We're only optimizing 1 BPM, but it makes a good job. If we switch to frequency domain, it's also a good job because this correction in time domain is done with no extra noise in the BPM. You can see here, this is the best reference variable for beam motion. And also, if you make an analysis of the RMSE of the deviation of the BPM, you can see you come to the same conclusion. It's a good correction because it's an easy case. A more difficult case, we have the same 6 BPM, the same 6 steers, but now we want to maximize the global deviation. We take all the BPMs, the 102 BPMs, and we define this reward here, which has to be maximized. And the agent has to face this very difficult problem, only manipulating 6 steers. We have some convergence here, we have some drifting problems of the machine, but nevertheless it worked. But in this case, the agent was not able to correct enough in time domain. This was a little bit disappointing, but in frequency domain, it did correct in a very nice way. You can see here in our reference beam motion variable, the red line is below. So we're here integrating the spectrum. It's not that easy to see. And also, of course, if you consider the spectrum of the global deviation, the red line here is also better than the baselines. Our disappointment with the time domain action has been faced with additional approaches, such as a model-based approach. In this case, we define a model that learns the harmonic perturbations by observation. You can define a function such as this one, and you try to predict the next BPM according to the previous position and the current correction. This supervised learning approach was very, 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 very accurate. You can see here that the R squared is much better than any baselines, including the meso response matrix. The nice part of this approach is that we can use it for example, this small algorithm, which is essentially the response matrix-based algorithm improved with a prediction given by the model. And you can see in this case, the time domain performance of the model is quite similar to the fast orbit feedback algorithm we use in the set the Q loop, but the frequency domain is much better. It means it was able to stabilize the orbit in frequency domain. Another advantage of this model-based approach we are exploring right now is that you can see in a nice way what the algorithm is doing, what the agent is doing. For example, going towards interpretability, which is an important feature in machine learning. You want to understand, to see why a model works. In this case, it's quite easy to see. For example, if you take the surrogate model predicting the next BPM position, and you calculate the Jacobian matrix of the neural network we're working with, which is differentiable almost everywhere, so you can do it with automatic differentiation, you end up with this matrix. And this matrix is, as expected, very, very similar to the response matrix measured at message 2. It means the linear part of the neural network predicting the next BPM position is, as expected, very similar, and it's accurate with respect to the theoretical response matrix. And furthermore, you can also analyze the standard deviation of the Jacobians and see where is this model, this surrogate model, learning the orbit in a non-linear way. As you can see here that the yellow points are more linear, so are correlations between steerers and BPMs that are learned in a non-linear way, which is also interesting information.
Luis, 2 minutes.
2 minutes. Wait, this is a very short case. Anomaly detection is also a central part in machine learning. In this case, we work with isolation forest, which is an unsupervised learning algorithm, very elegant and very easy. And we have developed a prototype which is ready for rollout in the control room. And furthermore, we have developed a sort of anomaly score for each feature, allowing us to make an assignation and see whether we have an anomaly, where is it located, which features are working bad at the moment. A very short example, and then I conclude my talk. You can see here, for example, in a use case and a proof of concept with all top-up variables of the machine, lifetime, current, injection efficiency. You can see here a normal point. You can see an anomalous point where the isolation forest says, okay, we have some anomalies everywhere. We have a negative score. But the most interesting part is that with our feature assignation coefficient, you can say, okay, in this case where we have a more or less anomalous point, why is it happening? And you can see here, in this case, we have a high anomaly at the average booster current, which was actually triggering our alert system. So we're happy with this case because the isolation forest and our feature anomaly score were able to recognize this anomaly in the booster current, average current, sorry, with no information about our alert systems. I conclude. I have presented first our central case right now, the mitigation of harmonic error perturbations with reinforcement learning, with a model-free approach and also a model-based approach we are going towards. I have also briefly presented our further case we are exploring, the use of anomaly detection in the control room and also with a more or less original system for feature assignation. Our next steps, of course, is further exploring of the model-based approach I have introduced, and also go towards interpretability. This is a very central feature, very central topic in machine learning, and also in order to gain confidence in such a context as such like an accelerator, it's very important to understand what the model is doing. So we are going also in this direction. You can find the references I have mentioned also in the talk. Thank you very much for listening, and of course open for questions.
Thank you, Luis, for this very nice talk. We have 2 minutes for questions.
I haven't seen any question either on WOVA or here. Luis, maybe, yeah, Marco, you want to so I was wondering, because you started with the model-free approach, then you go for a model-based approach. I understand that your model base is based on a neural network. So I guess you have to train the neural network offline before, right?
Not exactly. I mean, the model-free is also based on neural networks. DDPG is an actor-critic algorithm also with neural networks for the actor and for the critic part of the algorithm. So we are using neural networks everywhere. You can see here, actually, the configuration. And yeah, for the surrogate model, you can work offline, but in our case, what we did is also work online. So all the tests I have presented were done at the machine. So in this case, in order to train the surrogate model, we use the same CNQ loop we had. We excited the steerers with a random perturbation, with a randomization, with some probability, and then we learned live we observed live the reaction of the accelerator, and the surrogate model learned in an online way. Of course, this can be also done offline.
Okay, so that means that you continuously adjust the weights of the neural network all the time.
Of course, yeah. And in all cases, also in this case, well, no, in this case, we took the data and then we trained the network later, but we are also going towards a model-based reinforcement learning approach. And in this case, you have to do everything online. So the learning, the weight learning has to be done also online.
So my conclude question is that how do you ensure stability in your approach?
It's no way. You have to explore. You have to test. And especially in the model-free case, this is a very difficult approach because DDPG is a demanding algorithm, and the stability is only assured by testing and getting experience at the machine. So we have to spend many nights. You have to define where the maximum value for the steerers. You have to switch and fine-tune the parameters because you have no guarantee that the stability it's case depending, and you have many hyperparameters to test. In this case, with this final configuration, we achieved some stability. But for example, one reason by which we are going towards a model-based approach is that DDPG with more variables, if we go for all steerers and all BPMs, the convergence is very, very difficult. So this is the reason by which we had DDPG for a small case with only 6 BPMs and 6 steerers along the ring. And if we want to move for a global algorithm, observing and modifying everything, we will need probably a model-based approach in order to make the learning process more easier.
Thanks.
One last short question. So there are questions? Okay, by me, regarding the first part of the talk, would it be possible to use all the BPMs and all the correctors? Otherwise, if you just try to optimize and reduce, in average, all the BPMs, but in average, the BPM noise, this doesn't assure you that all the BPMs reduce their noise. It's possible to use. Yeah.
This is exactly the point. In DDPG, we observed everything in this case. So the reward is defined for all BPMs. So we are optimizing everything, but the state and the action we are observing and manipulating are smaller. Why? Because in DDPG, you need a smaller state and action space with larger dimensions. It's already a continuous space, so the convergence is very difficult.
Okay.
In the model-based approach, we are working with everything. Since in this small algorithm, this is actually based in the response matrix-based correction. So we are working with everything. We make the prediction and we correct all BPMs and observe. So we observe all BPMs and correct all steerers. So we are trying to find the midpoint between model-free learning and model-based foundation in order to modify all steerers and improve the performance in time domain, because in frequency domain, it was already good enough.
Okay. Thank you again, Luis.
Thank you very much.
Okay.
Okay. So let's go to this. Yeah, let's go to the second speaker. You can answer, Ryan. So he's Ryan Russell. Ryan Russell is an associate scientist at SLAC, National Accelerator Laboratory, as part of the Accelerator Research Division. He works on developing Bayesian techniques for improving optimization of simulated and realistic accelerators. He's also interested in how these techniques apply to advanced accelerator concepts. Today, he's going to talk about Bayesian techniques for accelerator characterization and control. Ryan, the floor is yours.
Yes, thank you so much. Is my screen sharing okay?
Perfect.
Okay, awesome. Thank you very much for the kind introduction, and thank you for the committee for allowing me to share my work today with all of you. So we are trying to, at SLAC, we are trying to develop algorithmic control schemes for particle accelerators. And instead of using neural network techniques, which were discussed in previous talks, We are taking, well, part of I in particular are taking a Bayesian approach to creating control algorithms for accelerators. So our goals are twofold here. We would like to automate routine tasks and improve performance and enable new capabilities in the machine. And these algorithms are challenged by the practical constraints and complexities of realistic accelerators, not to mention the inherent noise that exists in all facets of accelerator facilities. We'd also like to incorporate prior knowledge, either from physics or high performance computing cluster simulations or neural networks into our decision-making process. And then we'd also need to take into account scaling issues. And particularly for Bayesian type techniques, which I'll go over in a moment, these methods are especially useful for expensive measurements. So when it is very time consuming or practically expensive in some other way in order to make a complicated measurement. And so this technique that I will describe is advantageous when we have very expensive to evaluate functions. So the Bayesian surrogate model, instead of a neural network model, looks something like this, where we use Bayesian statistics to create a prediction of our function f of x at some input point x. We add in our observations into our model, and that will allow us to predict a mean and a confidence level everywhere in our input space. And we use a kernel function which describes a high-level behavior, the high-level expected behavior of our function. So for example, if we have a function that we expect to be fairly smooth in input space, then we specify that behavior in the kernel, and the model changes based on that kind of hyperparameter, whereas kind of a neural network has the connectivity hyperparameters. We have length, scale, and amplitude hyperparameters. And the advantage of this model is that it allows us to extract a lot of information from very few observations. And especially when it comes to optimization, where essentially we use a pseudo type reinforcement learning algorithm, where we have a function that explicitly specifies the validity of, or the value of future observations. So for example, if we are trying to exploit the model where we have a lot of confidence, then we can bias our algorithm towards exploitation, where we choose points that are close to the extrema of our mean prediction. Conversely, if we're looking to improve our model, we can choose to sample points that have large standard deviations, essentially large amounts of uncertainty, which would be the size to the left and right here. And so essentially what that allows us to do is balance between exploration and exploitation in our algorithms. And you can customize, as we'll see in a couple of slides here, you can customize these acquisition functions in order to vary the behavior of your pseudo reinforcement learning algorithm. So this is the process by which we call Bayesian optimization, where we create our statistical surrogate model. We feed that model into what's known as an acquisition function, and then we optimize that acquisition function in order to determine the next point that we were going to observe on the physical accelerator. And like I said before, we can explicitly specify the trade-off between exploration and exploitation. And then we inherently improve our model accuracy in our regions of interest, either near regions of local or global extrema, or overall if we are trying to characterize our function. So what I'm doing today is I will show two examples of how we are using these Bayesian optimization techniques to solve accelerator-specific control and optimization challenges. So the first is characterizing an unknown function. So for example, if you sit down at your accelerator and you want to start off by characterizing maybe the beam emittance or some other beam attribute with respect to some collection of input variables, you might choose to do a grid-like parameter scan where you specify the separation between grid points, the number of grid points, and the maximum and minimum regions. However, this relatively simple technique actually requires a lot of prior information about the function to be known in order to set those parameters. Essentially, you want to sample at a high enough frequency that you characterize high frequency behavior in your target function. You also need to specify the valid ranges subject to a number of different constraints. For example, your beam could go off your diagnostic screen or some other practical constraint. And then on top of this, if you want to scan multiple parameters, the number of points that you have to take grows exponentially, not to mention the complexity of your constraints in your system becomes very difficult to characterize beforehand. And so we use Bayesian optimization to create an automatic method of sampling these target functions without human intervention or prior information. So what we do is we specify a very specific acquisition function, and we term this entire algorithm as a Bayesian exploration. And it has three parts to it. The first is an adaptive sampling metric. The second is modeling unknown constraints using our data. And then the third is proximal biasing. And I'll go through each of these in kind. So the first of all, if what we do is throughout optimization, we can teach our Bayesian model the correct length scales or the correct frequency at which we expect our function to vary at. And what this does when we specify this first part of the acquisition function is essentially it'll cause the algorithm to sample at a higher frequency along the axes of our input variables that the function varies the quickest. So if we make an observation that our function varies the same with respect to x1 and x2, so the sensitivity of our target observation is equally sensitive between these two variables, then we have a uniform sampling essentially. But if our function varies much faster with respect to x1 than x2, it will automatically increase our sampling frequency along that first axis. The second part is modeling unknown constraints. So if, for example, we require that the beam size or some other characteristic has to be smaller than some maximum value, what we can do is model that separately and then essentially make a prediction as to what the likelihood that we will satisfy that given constraint. And we bias our acquisition function such that we reduce the sampling in regions where we're not expected to have valid measurements. The final term here is what's known as proximal biasing. And essentially what happens is it's very poor for an algorithm to be quickly varying input parameters in an accelerator because this, one, can be expensive since it takes time to change certain parameters. And two, if we have quickly varying parameters, that can screw up background processes that are maintaining RF phases or some other parameters. So that could screw up those feedback loops. Essentially, what we do is we bias our function to make small jumps in input space.
2 minutes,
and so
Brian.
I'm sorry?
2 more minutes.
Okay, great. So we did an experimental demonstration of this at the Argonne Wakefield Accelerator, where we are characterizing the beam emits using multiple slits. And we were able to demonstrate that our algorithm efficiently samples a 4-dimensional space much faster than a grid scan could sample 2-dimensional space. I'll skip this. The other application that we did was serial multiple objective Bayesian optimization, where we essentially are trying to balance the trade-off between multiple objectives and find the Pareto front in a serialized manner. And so we use an acquisition function here that calculates the expected hypervolume improvement of our Pareto front, which speeds up our optimization over other multi-objective algorithms, such as evolutionary algorithms, by a factor of 35 times. And so we are able to use this in a physical accelerator as opposed to a massively parallelized simulation. The last thing that I'd like to point out is that we've incorporated all of these Bayesian algorithms into a flexible optimization framework in Python that can be very easily used by external users that don't know anything about Bayesian techniques. And so this has been used for simulated and physical optimization of accelerators. And with that, I'd like to thank everybody for attending.
Thank you very much, Ryan. Questions now? Don't be shy. Check on the quality here. Okay, I just throw my first question to you. Is there any particular factor that you may highlight why you use these Bayesian techniques in comparison to other algorithms, like other machine learning?
So Bayesian techniques are extremely efficient because of the amount of kind of extrapolation and interpolation data or inference that it gives you. So by predicting both the mean prediction and the corresponding uncertainties of those predictions, we can significantly speed up optimization in both a local and a global sense. And so efficiency is really the name of the game when it comes to Bayesian techniques.
There is a question now on the QA from Joao Furtado. What are the next steps of this project?
Sure. So right now, what we're working on is kind of what you see on the slide here. So while Bayesian techniques have large efficiencies, when you scale it up to tens of thousands of data points, like you would in a neural network, the actual calculations, the statistical calculations that you have to do become very expensive. And so what we're looking to do is basically place this Bayesian type model on top of another surrogate model, such as a fast executing neural network. And so that will essentially scale the Bayesian technique without having to have very expensive calculations involved and slow down the algorithm itself.
Okay. Marco, you want to add something? Or?
Yeah. What was the main issue you encountered when you passed from theory and model simulations to the real machine?
So I'm sorry, could you repeat the first part of your question?
What was the main issue, the main problems you faced with using this algorithm on the real machine instead of on the simulators?
Right. So actually, the Bayesian technique is actually more well suited for realistic accelerators than it is for for simulations, mainly because it inherently takes into account the noise of observations in experimental settings. Not to mention the fact, especially with respect to constraints, the fact that you can specify nearly arbitrary constraints without prior modeling beforehand makes it very easy to implement in a variety of situations. Whereas kind of neural network techniques requires lots of training data, and so there's a lot of upfront cost to using that type of algorithm. Bayesian techniques basically give you no startup costs, and you're able to solve kind of almost any kind of low dimensional problem very easily. And so it's honestly a little bit more difficult to use them in massively parallelized simulations than in physical accelerators.
Thank you.
Okay, thanks.
Okay.
Thank you again, Ryan. Marco, you.
Yeah, can pass to the next speaker, Stefano Pioli from INFN LNF Frascati, Italy. Is going to talk about machine learning based middle layer for autonomous accelerator operation and control. Stefano is a control system engineer with a PhD in particle accelerator physics and a broad experience on design and development of particle accelerators control systems for nuclear physics. He is a member of the control system group of the accelerator division at the Istituto Nazionale di Fisica Nucleare Frascati National Laboratories, with focus on high-level software and functional safety, and responsible for the Singularity project. Please share your screen, Stefano.
You're muted, Stefano.
Okay.
Okay.
And you?
Yes.
Okay. So I will introduce my work for the context of the Singularity project for the development of middle layer machine learning based algorithm for the autonomous operation on particle accelerator. As general capability for this system, we're looking for machine independent to would be suitable for any kind of accelerator, and our general independency from device misalignment and the performance drift in order to work with a commissioning accelerator or with old machines. In this talk, I will talk about our tools on reinforcement learning based for autonomous particle beam tuning, energy tuning, and for charge optimization. That's our brief introduction. Here at Frascati, we have the Athene complex, in particular the LINAC electron and positron LINAC, able to work up to 500 MeV of electron and positron with 4 RF sources. And the machine have 30 years of operation. So as you see here, comes with a very old control system that have been updated during the year. Now works with Linux machines in the virtualized system. And we work to develop a system, a middle layer framework with a memcached communication to acquire data to the middle level Python middle layer and push command with a REST socket. In this context, so we apply our Markovian decision process tools, and we focus on the 2 modulator at the end of the LINAC, so where we have both electron and positron. And we designed the environment working on both phase and power for the 2 RF sources. So defining the range of operation in order to ensure the safety of the system and doesn't allow to have moving the machine in dangerous point and break some machine components. And then we define also the accuracy of the system that we can allow or that we cannot tolerate. And the system, it's feedback with an otoscope that give us the readback about the energy of the particle beam. the agent is a Q-learning. It's a Q-learning algorithm that provide rewarding variable in function of the difference between the target energy of the working point that we are looking and the energy of the particle beam that we are operating. Everything mitigated with an exploration exploiting policy balanced with an epsilon grid strategy. In this moment, we work with a huge and slow state action matrix based on a static array in order to allow easy debug of the code. This should be upgraded briefly with DQN. And as you see here, each possible action comes from the combination of all the possible state of phase and power of the two sources, and the state comes from the possible states from the oscilloscope. We run the training of the system with 300 episodes, and starting with a random phase power set point and moving with a Q-learning algorithm. As you see, we reach the training of the system within 1 kilostep. That for us means be able to train the system with 1 week of beam shift. And this it's a really interesting result because it's a reasonable time to dedicate to this kind of algorithm to train an autonomous tuning. And this is also interesting because we're working on a very old accelerator, demonstrate that we are suitable for not only new machine, but also with accelerator where drift, misalignment, and loss of performance move device far from their nominal performances. After this, we introduce a similar tool based on charge optimization. We work always in the second part of the accelerator where we have a positron and electron. In this case, in the environment, we have 8 quadrupole magnets, and so there we control the power supply current, and we feedback the system with 2 beam current monitor. In this case, we are going to optimize the charge, but it's some way it's also a trajectory optimization tool. Also here we have a rewarding variable in function of the difference between the desired charge ratio and the current charge duration between the 2 beam current monitor. And we perform in the same way that static state action. We fulfill the static state action matrix. Also here you can see that we proceed with 300 episodes for training, and we converge in a stable result in 2,000 steps that are about 2 weeks of beam shift. Also in this case, it's something that we assume reasonable for this kind of application. And about the conclusion, we have validated this performance learning tool suitable for operation not only in normal operating facility, but also for the commissioning one or for old complex like Daphne. The huge point of this tool is that are not related to specific performances of parameter of the devices. So we just have to define the lattice of the accelerator and the limit of the parameter for each device in order to have safe operation. And what we get till now, the training period is reasonable for dedicated beam shift to train these tools. And we will perform first fully autonomous run in Daphne in the next weeks. And we always update with DQN networks in order to have a better memory management and leave this static state action metrics. Thank you.
Thank you, Stefano. Interesting talk, and thank you for being fast. There are some minutes for questions. Raise your hand on the Zoom. So meanwhile, I have one question. Did you do some comparison with other optimization algorithms, the standard neither mid, gradient, power, etc.?
This is something that we until now we work. It's working on Daphne. We work with the reference working point module that we have with the MAD simulator. And until this moment, it's we have a fully agree with the result of the machine learning and the MAD simulation.
I mean, if you made some comparison of performance between this reinforcement learning and the classical methods.
This is something that we have to investigate.
Okay.
We wait to have a full test because with simulated one, we are confident of the result because the machine is stable after all this year, but we wait to have the real data to check the performance.
I have another question. Please.
I have another question, Stefano. I understand that you plan to really experiment the performance now in reality, right? Up to now is simulation.
It's not simulated. It's from acquired data from the accelerator and sampled with the performance that we have from acquired data. It's an offline testing until now.
Yes, offline testing. So now you will connect online. And that means that what is the degree of confidence you have in the robustness of the solution?
Currently, we checked with the tablet performance of the accelerator. We are within the 5% of tolerance respect of what currently we get with human operators.
And what about the robustness? How do you measure the robustness?
Of the.
Are you going to be stable? How do you evaluate the stability of your system?
This is something that we are interested to test with this dry run on real machine.
Thanks.
Thank you.
Other questions? Just one last by me. What's the reason why you need so much time to I heard about 2 weeks of shifts.
First because the CAMAC system that are still present on the Linux will operate slowly the accelerator. So we expect to take less than 1 week or 2 weeks in function of which tool that we're expecting, but we expect to use a couple of days, but we are.
So how many measurements can you do in this time?
This time it comes from performance measurement of how much time we require to apply a command on the CAMAC system and have the feedback on then multiply for the number of steps that we expect from the algorithm.
Okay.
Plus confident spare time.
Thank you again, Stefano.
Thank you.
Okay, so let's move to the last talk of the track. Jonathan Edelen is an accelerator physicist. He specializes in thermionic cathode guns and space charge effects in low energy electron beams, RF control systems, machine learning for anomaly detection. Currently, John is focused on building advanced control algorithms for particle accelerators, including solutions involving machine learning. And I think I give you the floor for your talk, Jonathan.
Okay, great.
Well, thank you everybody for joining for this talk, and thank you to the organizers for allowing me to present some of my work here today. Today I'm going to be talking about some recent work we've been doing to build machine learning based tuning and diagnostics for the ATR line at Brookhaven National Lab. And this is an ongoing collaboration funded by a Small Business Innovative Research Grant through the Department of Energy, Office of Nuclear Physics. So just a quick overview of kind of what we're interested in doing here. So in general, we classify accelerator time into sort of three areas, and we're primarily interested in sort of optimizing the use of accelerator R&D time and optimizing the use of beam time for experimentalists while minimizing downtime. So when it comes to anomaly detection, generally speaking, we're trying to do either predictive maintenance so that we or predictive anomaly detection so that we don't have as much unscheduled maintenance. And then for machine tuning and optimization, we're trying to get the best performance out of the machine, either during accelerator R&D time or during beam time for experimentalists. So we've been exploring this using neural network-based inverse models, and I'm going to just talk a little bit about the two different applications of neural network-based inverse models and describe sort of the background, and then I'll go into some examples. So the first sort of example of neural network-based inverse models is a very typical example that you see. You have a set of BPM readings, and then you have a set of corrector settings, and you basically train a neural network to take a given BPM trajectory and tell you what the corrector settings ought to be to optimize the beam position, the beam trajectory, either along a transfer line or along or in a ring. And here I'm showing an example from the ATR line that we produced a couple of years ago. This is basically you train the neural network-based inverse model on the relationship between the BPMs and the correctors, and then you say, okay, I want the beam to be on axis throughout the entire transfer line, and sort of test those corrector settings on the simulation. And this is something that we've been doing for a while. There's a number of efforts to sort of apply this method across accelerators, and this is kind of the classic example for inverse model-based tuning. And yeah, so this is a supervised learning method. The other is to use inverse models as a starting point for optimization. So here, maybe you use an optimization tool that is a model independent approach, right? And then you train a neural network on sort of a broad range of settings or a broad range of parameters, and then use that as a prior to start the optimization, and then run the optimization to find sort of the local optimal configuration. And both these methods are sort of supervised learning approach where you have a known relationship between the inputs and outputs. The other thing that we've been using inverse models for more recently is for anomaly detection as a diagnostic tool. And here, this is more of an unsupervised method. So in this case, you have a set of BPM readings and you have a set of correctors. And again, the BPM corrector relationship is known. And then you use the inverse model, given a set of input BPMs, predict the correctors, and then compare that to the actuals that you see on the machine. And what this can be used for anomaly detection is if you have an error in another system, if you have an error in a cavity or an error in a magnet, in a quadrupole magnet or another type of magnet, sextuple magnet, that's going to change the relationship between the BPMs and the correctors. So now when you test the inverse model that you trained during sort of a known configuration against sort of new data, then you will have errors that show up in the predicted corrector settings versus the actual corrector settings. And then you can use that to sort of flag anomalies and try to understand where you have errors in the machine. So the assumption here is that the model errors are caused by other beamline elements, that it's not due to the BPM corrector relationship changing. So that's sort of baked into this approach. And then the other assumption is that if you have an error, that the signature that you see of comparing the predicted correctors to the actual correctors is unique, that you don't have sort of degenerate solutions to the errors. And if this is successful, then the next thing you could do is potentially use this for tuning. You could adjust, tune sort of other parameters, tune a quadrupole to minimize corrector strength errors in your inverse model type of thing. So we've been applying this to the AGS to rect transfer line, and just a little bit of background on that. So this is the accelerator complex for the relativistic heavy ion collider at Brookhaven. and then the AGS to RIC transfer line transports the beam from the alternating gradient synchrotron into the collider ring. And it consists of sort of two initial beam lines, the U and the W line, where that's shared by both rings in the collider. And then there's the X and Y line, which inject beam into the yellow and the blue and yellow lines respectively. And this is just a schematic showing you the different sort of components in the beam line. There's a vertical drop in the beam line, which introduces some coupling. And then there's also a number of apertures in the beam line as well. So on the bottom, I'm just showing a plot of the beta functions along the beam line, just to show an idea of how sensitive it is to energy deviations and errors. And you can see that the transmission drops quite dramatically for an energy, a fairly small energy error, which is just due to the fact that we have tight apertures right around the 250 meter mark. There's a pretty small aperture that we have to deal with. So making sure the beam is properly centered in the transfer line and making sure that the optics are corrected properly is important for operating the transfer line. Okay. So the study that we did was primarily in simulation, and we're in the process of working on transferring it to the machine. And the data generation is done in two different steps. So there's the training data generation, where we randomly vary correctors and we have all the quadruples set to the design values, run that through a MADX model, and then get the BPM settings or the BPM readings. And then there's a test data set generation where we also randomly varied all the correctors, but then we varied quadruples one by one and in increments ranging plus or minus 20% of their design value. So you just essentially doing a sort of systematic error study on all the quadruples, while also randomly varying the correctors and then getting the output BPM readings. And this should give you sort of a broad characterization of the data that's being sort of a number of different configurations for different beam trajectories in the ring for different quadruple settings or in the transfer line. So we trained the inverse model using 5,000 samples from the randomly generated corrector strengths and initial beam positions. This is just a standard feed-forward neural network. There's nothing too fancy going on here. And we did have some issues with degenerate solutions. So for the correctors were not very well predicted by the inverse model. And through some exploratory work, we basically determined that this was degenerate solutions. So the model is not invertible for those correctors. We decided to exclude those from this particular study just so that we could proceed with trying to understand how the model can predict quadruple errors. And these are just some information about what we used for how the model is constructed. And then on the bottom right-hand plot, I'm showing the mean squared error for each one of the initial positions and the corrector settings, sort of element by element for the training and validation set. So the bottom orange is the validation set and blue is training, same with the top plot. So then we tested the inverse model on the data where we had systematic errors in the quadruples with random changes in the BPM and the corrector settings and the initial positions. And we did this for two different configurations. So I wanted to understand whether or not if we had random initial position errors, how that would be different than having just a static initial input. So if you have the beam comes in out of the AGS just at some position, and we have random sort of changes in the corrector settings, how those two would compare when trying to predict quadruple errors. So the right-hand plot I'm showing for a single quadruple error. So this is just, we picked one of the quadruples in the sort of middle of the beam line and had an error in it, and then compared the predicted corrector settings versus the ground truth corrector settings for the three different cases. So the black is the baseline model trained without any quadruple errors. The red is with a single quadruple error, but with random initial position errors as well. And then the blue is with single quadruple error without random initial position errors. So you can see there's a very clear signature that there's an error, that the model says, okay, there's something different about the relationship between the BPMs and the correctors. And that also varies along the beam line. So if we look sort of from the top left to the bottom right, these are moving along the beam line in sequential order. And while all of them show some error, there are definitely correctors that are not predicted as well and show significantly larger error.
John,
and then if we look at the sensitivity,
2 more minutes, John.
I only have like 3 more slides. So if we look at the sensitivity of each quadruple prediction as a function of the correctors. So on the left is showing the corrector errors, and then on the bottom are showing the quadruple that was varied. And see that each corrector has a unique, each quadruple has a unique error signature that can be shown. You can look at it on the plot here, and it does a pretty good job of detecting these errors. So we're in the process of transferring this onto the machine. So the first thing is to collect BPM and corrector data from the nominal machine configuration and train a neural network on it. We had a short beam study period. So we're able to collect sort of a small amount of data and train an initial neural network on that data. This is showing the results of that inverse model training. So we're sort of in the process of identifying what additional data we need to collect. We have some correctors that don't really predict very well from the data set, and we think that we just need to collect a little more data in some areas, but we also have the same problem with degeneracies as we did in the simulation model, so we need to figure that out too. So just sort of concluding, I didn't talk about this photo toy problem in the talk, but it's in the paper. We did, before we went into the ATR study, we did a study on just a simple photo lattice just to show sort of how well this would work in principle, and then we scaled it to the ATR line at RIC. And the idea here is that we have some success showing inverse models predicting or identifying errors in quadruples without explicit knowledge of the quadruples, of the quadruple errors. So this is encouraging, and we're sort of in the process of transferring that to the machine. And we're also going to try to use this in tuning studies to try to optimize or minimize machine errors by using this inverse model. Okay, thank you very much.
Thank you very much, John. We have time for one question. Any question in the audience? Nothing there? Marco, otherwise we just conclude here.
Just one. So I know that you are working with different accelerators. Do you find differences in the application of these algorithms in different scenarios? And are these machines different in terms of reproducibility, for example?
Yeah, so reproducibility is a great question. I know the ATR line is very linear in general. It's a robust beam line. It's been around for a while, so we expect that's going to be fairly reproducible. But there's definitely had some experience working with machines where they change something, or they're constantly sort of going into a maintenance period and saying, okay, we're going to move something around. Like the injector at JLab, for example, they're just coming out of the maintenance period soon, and they have moved some elements around. And I think this happens like on some schedule, right? And especially with some of the test accelerators at Fermilab, I know this has also been a case where things change because it's a test accelerator. So it sort of depends. I think with some of the older accelerators or some that are sort of more stable, it's easier to get reproducible results. But if things move, it's hard to, yeah.
Thank you very much, John, again. Should we close it here, Marco?
Yeah. Please.
Okay, so thank you very much. We conclude this feedback control track. We give hand or pass the relay to the control system infrastructure track. Thank you very much.